Okay, we are back to the second half of the mighty presentation of Mighty Ali. So, ask questions, even if it's short. Please use the microphone. The remote people really complain. They don't understand the question. They don't hear the questions. It's on mute.
Oh,
so now it should work.
okay,
Yeah.
that's fine. Thank you very much. For extension of the same solution for outdoor relays, the system model would look like this, and you can refer to this paper for details. Okay, now coming to what the second solution, SON solution. This solution is focusing on even larger term dynamics. The reason I'm saying it's larger term dynamics because the parameter we are going to adopt is cell size. So it's not reasonable to change the cell size every few minutes because obviously from for hand over parameters. So the solution would be useful for larger dynamics, for example, variations over day and night, or permanent hotspot or shadowing. Okay, let's look what we have here. This solution is focusing on load balancing. Previously, we were focusing on spectral efficiency optimization, and now load balancing, as you have seen in previous presentation, even in this presentation, has been identified in one of the agendas by 3GPP, NGM, and also some industrial products are trying to come up with this feature. So looking at the literature, there is a lot of work you can find in load balancing, which can be categorized in 4 different categories: resource adaptation based load balancing, traffic shaping based load balancing, relay station based load balancing, and coverage adaptation based load balancing. Does anybody have a question about them, or everybody understands?
Maybe you could elaborate.
Okay, elaborate. Okay, so this resource adaptation based load balancing means you allocate resources to the cells which are overloaded more by borrowing, for example, channel borrowing coming from classic GSM systems to UMTS and then to maybe LTE. And traffic shaping means you adapt your call admission parameters such that you don't accept more calls from in the cell which is already overloaded, or you trigger handover, artificial or enforced handovers from the overloaded cells to other cells. Relay station based load balancing means you'll find some papers which have tried to use relay station as a load balancing agent by kind of tunneling your traffic to a neighboring cell, because relay station can cover a local area, and then instead of providing a backhaul to the local cell, it can provide link with another unloaded cell, and effectively can channel your traffic to neighbor cells for a better load balancing. Coverage adaptation based load balancing means you change your cell size for optimal traffic distribution. There are 2 different actuators which are used for coverage adaptation. First is through antenna adaptation, tilt, or say azimuth, or even maybe some kind of radiation pattern adaptation. And power adaptation means you simply change the power of your transmission power of your base station. It should not be confused with the power adaptation of data signal. Data signal is power adaptation of cell ID signal, reference signal only, which will let the users know that which cell I am connected to. Okay, so this particular work is based on this reference signal power adaptation, and again the solutions which have been proposed so far are mostly centralized, and that's why they tend to have low agility and heavy signaling is required. But the solution we are going to discuss here is again distributed, and it relies on multiple mechanisms: coverage adaptation, resource adaptation, and beam switching. Beam switching does not mean beam forming here. Beam switching means beam switching on the relay station. If relay station is allowed to change its parent base station. Okay, I won't go into that much details as I went over the previous solution and the mathematical details, but again, the steps being followed are almost same. Here the problem is formulated. Problem is classic problem. We want to minimize the call blocking rate, B, which is a function of number of resources in a cell and amount of traffic. This B is classic blocking function. Okay, and the constraints we have is that the total traffic, of course, will stay same, and total traffic in the total amount of resources in the system cannot be changed. We cannot have a call for more resources. We have to live with the resources we already have. Okay, so here we somehow, means it's very simple. It's not that complicated as the previous solution. We are able to find the solution which looks like this. Means this is the condition which should be met. But problem with this condition is that it has to be implemented for all the cells. This condition says that there's this ratio between the amount of resources and the traffic offered to the cell should be maintained over all the cells. But again, this here the problem is it talks about all the cells. We cannot practically implement it. If we implement it, we'll end up with the same types of solutions which we have in literature. So to break it down, we need to play around it. We play around and we solve the system-wide problem, and we make it to change it to this form. And this is for optimal, for minimum blocking, you need to have this much traffic in each cell. Okay, and if TT means this is the total traffic in the system, this is the number of total channels in the system, this is number of resources in your neighboring cell, and this is number of resources in your own cell. So for every cell, this condition should be maintained. But again, it's difficult to maintain it. And if you look other way around, then either you can have control on traffic, or you can have control on resources. If you are going to use traffic adaptation, then this is the solution, but global and central solution. But if you are going to use resource adaptation, then this is the solution. Depends which actuator actually you are going to use. But to get a practical solution, again, I would say practical solution, not exactly optimal solution. Practical solution, what we do here is, just like we had the concept of triplet there, here we have a concept of supercell. Supercell in the sense means you can make a cluster of cells. It does not have to be dynamically made. If you can choose to have a dynamic cluster of cells, but again you will be trading off with the agility of your solution because it has to be done on the runtime. Simply what you can do is, in the heterogeneous network, every base station can act as a supercell, assuming that it has multiple sectors or multiple cells, and also multiple relay stations and multiple maybe femtocells. For example, this is the location of a base station. It has maybe 6 sectors and then 3 relay stations or femtocells under it. This is a very symmetric scenario, but it's just for representative purpose. And then this can be considered as a supercell. Of course, if you increase the size of your supercell, you are going towards the optimal, closer to optimal. But you can, and the solution we are presenting here is can have as small supercell as 1 base station with 3 of its sectors and few of its relay stations if it has relay stations. So this would be a supercell. Okay. Once we are clear about this concept of supercell, then we can simply assume that we don't have to, based on that inspiration we have, we don't have to kind of go for global optimal solution. Okay, what if we balance the traffic within each supercell independently? This is how we'll start. We'll go towards balancing the traffic among the supercells later, but this is how we're gonna start. So if we do that, then the solution. Sorry for this low kind of resolution, but this is the same equation. But here we, instead of having the channels and traffic in all the system, we are scaling down our problem to supercell. We are assuming that our system is, each supercell is separately a system. It's similar to where in natural system we rely on local observations only, and on the, this is the key behind having a distributed solution. Okay, once we have that, then what we can do is we can implement these two conditions using any of these 4 SO functions. Unlike the previous solution, we had just one SO function, which was tilt optimization. Here we can have 4 SO functions. For example, first is coverage adaptation at base station. Base station can change its coverage to have effectively the number of users, which will make keep the blocking into minimum. Or relay station can change its coverage. Or access link adaptation. Access link means the base station. If I go back. Sorry. For example, this relay station is connected to this base station, but this, for example, this relation is connected to this base station. But if this base station, a relay station has a switchable antenna, then it can be connected to this relay station. So this will allow us for a traffic overflow or load balancing, inter-supercell load balancing. But the result I am going to show would be just based on intra-supercell load balancing. So when we have this SO function, there needs to be an algorithm based on the analytical expressions we have. So this is a heuristic algorithm which will carry out this load balancing. The idea behind it is in each supercell, and the base station will be observing the blocking, and when it observes the blocking above a threshold, it can check for the conditions of optimality. If that's not, this condition is met, then this is the SO function should invoke, and if this condition is not met, then this is the SO function. Same is true for the other way around. This is on the access link. This is on the coverage link. Access link means the link between the base station and relay station, and this is a continuous loop, but you can again put some weights and slow it down based on your own requirements. So this is the solution, and then we do the performance analysis. These are our simulation assumptions, quite detailed. You can look at them later, and this is what we get. Here, let me explain what is happening. What's happening is, this is we are logging call rejection phenomena. We are logging how much percentage of the users don't find a free channel for a given user distribution and traffic rate. So without any load balancing, you are able to calculate them analytically as well, but the reason we are putting it in a system level simulation to have the impact of the factors which we cannot capture analytically. But without any load balancing, 4% of the users will have to face, the blocking, or the hard blocking, I would say, hard blocking will be as high as 4%. But if there is a load balancing solution based on supercell in place, this will be, blocking will be reduced to almost 1%. Okay, but this is based on distributed supercell. I mean, in each supercell, it's just changing its own cell sizes within the supercell sectors to keep the number of users to the optimal value. And the reason we chose this definition of supercell is that because inter-sector handover is trivial. You don't have to kind of do a lot of processing, and you don't have to do signaling, and it's not a overhead on the core network as well. So if just you can afford inter-sector handover, you are able to reduce your blocking substantially. Okay, and if you compare it to the globally optimal solution means, if you go back, instead of implementing it in supercell, we implement throughout the system. Then this is what you will get. So analytically means by putting in the blocking evaluation formula, you can get for a given number of users, given number of channels, you can see how much blocking should be occurring. So 1% is the blocking, but since it's a simulator and it's random, call arrival rate is random, so you have this fluctuation. But this 1% is the blocking which would be there anyways for this amount of users and this traffic.
Can I just ask? It seems, I mean, you're introducing relay cells essentially, right? Sorry, the difference between the red B curve and the blue A curve is the introduction of relays?
No,
or no? Sorry, okay, it's
it's just coverage adaptation.
Oh, okay.
The load balancing. But I'm
Okay.
trying to say is the solution we proposed, it has the algorithm is valid for relay station as well. If you have relay station, you can avoid the blockage on the access link as well.
Okay.
But the problem is it's difficult to simulate. At least I did not spend much time to simulate
Right.
the relay station and access link altogether. I just simulated it on the coverage links.
Mm-hmm.
So this is just on coverage link, and it's invoking just the coverage adaptation
Right.
as a function, not relays.
Right.
So what I'm trying to say, means what is the difference between the two curves is that in this curve, there is no load balancing in place.
Mm-hmm.
Okay. In this curve, ideal ICC, so ideal centralized load balancing is
Okay.
in place. Means you can say classic solution.
Mm-hmm.
You can calculate what should be the optimal traffic for a given number of resources in a cell to give you average minimum blocking system wide. Why does the blocking rise? Blocking rises because you have 100 users in a system, 10 cells. 2 cells contain 50 users, rest of the cells containing only a few users. So these 2 cells will have high blocking, and your average blocking in the system will increase. So there should be a mechanism for the load balance. There are a number of mechanisms, and one is that centralized load balancing. You assume that there is no limit. You can change your cell coverages such that you will always have optimal number of users to give you a minimum average blocking based on that.
Yeah, what would be interesting to see is maybe two other insights from this graph. I'm not sure whether you have more. But the first thing is to get the CDFs of the blocking percentage, because I think it's spatially very non-ergodic, just as you said.
Yes. It's
So you're averaging over everything, so I think you're losing a lot of advantage.
I have spatial graphs. I have also in terms of energy, because when you are changing your coverage, you might have to transmit on a longer distance for load balancing. I have that, but in this presentation I haven't included them.
No, what I mean is you take a slice for 100 users and you plot the CDFs rather than the average blockage percentages.
Yeah, this is that's another way to present the result.
Yeah, I think that would be the more interesting one, because you're averaging over non-ergodic scenario, because it's highly unbalanced, your whole system. See what I mean? You're comparing a bit apples and oranges here. With the load balancing, kind of average things, that's okay. So the lower one is probably the correct one, but the B one.
No, means if you look back at the formulation and the solution itself says that each there should be a ratio between the traffic in a cell and the resources, and this ratio should stay constant throughout the system. Only then you will have minimum average blocking.
There's no question about the goal and how you do that.
Yeah.
It's just the way you present it. This is what I mean.
Yeah, I'm trying to come to that point. What I'm trying to say is this solution itself ensures that there is fairness among the cells in terms of blocking. You won't be able to get minimum system-wide blocking, average blocking, if there is one cell with high blocking and other cell with low blocking. It's because of the nature of this Erlang blocking formula. Erlang blocking formula solution, when you solve it, you see that the average blocking will be minimum only when in each cell the ratio between the resources and the traffic is constant. Means the difference.
But this is after your SON operation, not before.
No, of course, after the SON operation.
Yeah, that's what I'm saying. The curve down there, that's fine.
Okay, yeah.
So
yeah.
the median of the CDF will coincide with the average of this curve.
No, I get your meaning.
But
Means
and the other
without this, yes, maybe I think I have some slide. Let me see. No, I don't have.
Okay. The other one which would be interesting is the temporal evolution, because I think that's one of the biggest advantages. I mean, just plot how it stabilizes over time if you take out one base station, or you put in, or you artificially increase a hotspot over time. Because I think one of the big advantages is not only to become more efficient, but also to be able to self-configure over time if things go wrong.
Yeah, actually in the detailed work, some aspects of what you are saying are covered. For example, this time analysis, the fact that how it will impact the interference, how it will impact the energy consumption, and how much users will have to actually go from one supercell to other is covered. But here, what I'm trying to portray is that we don't always have to think in terms of global optimality to get something working.
Right.
Yes, even with this simple solution, which is very simple to operate, because you don't have to even do handovers between different supercells. So you can just take any one site and make them balance the traffic among the cells or sectors and the relay station that site is taking care of. And with this model of just assuming that only 6 sectors are there and 3 relay stations, you can have this much reduction. And if you would have done it globally, then the reduction would be this much. So there is a very small gap between these two. Yes.
Is that the nature of a supercell that you simulate, the ones you show, or is how does a supercell look like in this simulation?
Yes, this is the simulation results are based on this supercell. If you change your supercell, reduce your supercell to, for example, 3 sectors, you will lose little bit gain. If you increase your supercell size, but you see the maximum you can get is this. Okay.
Yeah. This is kind of the best case scenario, right?
Yeah. This is the best case if you do forget about supercell and you are doing load balancing system wide. Hypothetically, that's why I put ideal central.
So those green circles, were they femtocells or?
No, femtocells or relay stations.
Or relay. So what I'm trying to understand is what's the effect of the location of those femtocells on this result? Suppose they are say random or something.
As long as they are within that supercell, the location doesn't matter. As I said, this is very for graphical representation symmetric situation, but within this femtocells can be here, or anywhere.
Okay.
But as long as they are able to coordinate with the main base station, and main base station is able to tell them that you should have exactly 3 users, and this base station should have 4 users. This sector should have 6, 8, 9. So it needs to tell every cell in the supercell the exact optimal number of users. As long as that's true, you will be able to improve your quality of service. Your users, users won't be complaining. But and if you prefer to go in a classic way, then here in the previous result I was unable to show because the analytical expression was quite cumbersome to have a global solution. But this is simple expression, so I am able to implement it, and even analytically you can see that for a given traffic, what is the minimum blocking you can get. So minimum blocking is 1%, and if for example, if they would have in 3 sectors, maybe you will be somewhere here. So if you reduce your supercell, but what I'm trying to say is, this is, even with this supercell, you can get very close to the optimal solution. Yeah, this is the optimal gap, which is almost negligible. And one important means this, you might be wondering what are these graphs. These are actually soft blocking. HB means hard blocking, and SB means soft blocking. If if I want to explain, I would explain it like, hard blocking is when your call rejected because of the fact there is no free channel. Soft blocking is when your call rejected because of the fact there is a high interference. Okay, so here because we have 6 sectors, so we already have low interference, but your interference will depend on the frequency reuse, not on this algorithm. But why I have put it here is to show that, means your if you see here in the red curve is when you don't do any load balancing, but when you do some load balancing, there is a slight increase, just this little bit increase in the soft blocking. But your central solution actually gives you more soft blocking. It will have negative impact. The reason behind is its power adaptation will propagate throughout the system. With this supercell concept, the power adaptation is going to be confined within the supercell, and it's not going to change much the interference. So in terms of capacity, if you want to see, means if you log on grade of service and you want to see, okay, for same grade of service, how much increase you will, means how many more users you can accommodate. With load balancing, maybe you can accommodate two times of the user which you could before, and this solution.
Excuse me. I have 2 questions. First, is there any problem in the interference inside the supercell? If you return to the supercell structure.
Let me see. The frequency reuse parameter, I think, as long as I remember, the frequency reuse is 1. Yeah, I know. Means you mean here.
The interference, yeah.
Among the sectors, yeah.
Yes.
Yeah, I'm trying to see here. Frequency reuse, if it's the, let me see. I think it is frequency reuse 1 or 2. The definition is, yes, frequency reuse is, no, this is frequency transmission model. Horizontal. That's amazing. I did not put frequency. Yes. 3 adjusted blocking. Anyways. Yes, frequency reuse, I think is 6. Means there's no interference, I'm assuming. But I have different results where you assume a tighter frequency reuse, you will already have higher soft blocking. Okay, but here we are not trying to reduce interference. We are talking about load balancing. If you already have higher interference, the point is this solution will change it slightly. If you already have low interference, because your frequency reuse was, or there is some coordination mechanism, the purpose of this plotting this soft blocking here is that you will have little impact, because you see still with the load balancing in place, your curve is lying down there. But I have solutions where if you have frequency reuse of 1 and there are only 3 sectors, then soft blocking looks like 50%. Already it's 50%. But when you implement your load balancing solution, it will go to say 53%, 54%. But your load balancing will act like the same. Okay. But the problem is when you will have high soft blocking, the gain you get by load balancing won't dominate, because your users would be, most of the users will be blocked by interference. They are not being blocked because channel is not physically empty. They are being blocked because the channel is empty, but there is high interference. So this solution has to operate for load balancing on top of assumption that there is already some mechanism for interference. But it won't affect substantially your already in place mechanism for as long as you are using this supercell, as long as you are limiting your power adaptation within a geographically confined area. Yeah, that's the point.
And why the curves are not that smooth?
Why the curve
are not smooth?
Means if you look at this x-axis, what is happening is this here the blocking is 0 because there is no user. As the simulation starts, users are arriving, okay, but they are arriving and they are leaving as well, okay. So this is the dynamic simulation in which users are arriving and leaving, but based on their exponential call holding length, okay, it has to go smooth after some time, okay, but it won't be straight line exactly because users are still arriving and leaving. Getting my point? Have you done some dynamic system level simulation on call blocking? So you understand, you model traffic with two parameters: arrival rate, call holding length. Your arrival rate is Poisson, and holding length is exponentially distributed. Okay, so these two parameters you set them to get a typical amount of Erlang traffic. When you set that, since it's a random variable, so random number of users are arriving, they are staying, means they are holding the channel for random length of time, but still they have average, means it's a IID process. So in the long end, you're going to get a stable blocking, but not a straight line.
So is averaging going on?
Yeah, it's averaging on a running average, it's a kind of a running average. Yeah. Are there any other questions? Fine. Okay. Okay. So let's move towards even longer term dynamics. I don't have to give another. Should I give another example? What kind of dynamics means? There can be winter. There can be social events, festivals, or economical changes, and the system should have capability to adopt them, adopt according to these longer term, very long term dynamics, for example seasons or demographical changes, without the need for manual intervention. This is the idea. But here things change a little bit more drastically than we have been dealing before, because here the time scale matters a lot. Because the most of the solution you'll see, again considering shadowing, fading, and scheduling parameters, power adaptation, and they are all just dealing with the parameters which are effective on short time scale. But when you look on the time scale of 6 months, or maybe a quarter, a season, a festival, then you have to, your optimization parameters have to be relevant. The optimization parameter which affects system performance on a longer time scale is frequency reuse. It's different than scheduling. It's different than radio resource allocation at a microsecond or millisecond time scale. It's the deployment architecture. How many sectors did you put? What was the tower height? What was kind of transmission powers? But we have dealt with the transmission power on medium time scale. Bear in mind that any solution which could work on a shorter time scale could be extended towards a larger time scale, but we cannot go vice versa from larger to smaller time scale because of the agility issues, natural constraints. You can understand that. And also the number of relay stations, for example, if we have in a heterogeneous network, that will affect your long-term performance. but first we need to define the performance itself. Classically, it's throughput, energy efficiency, rate, fairness, blah, blah. But on scale of 6 months or quarter, these terms do not remain as meaningful as they are in the classic sense. We need to come up with things which are more directly a function of these long-term parameters. They are determined by them rather than the short-term parameters like transmission power scheduling schemes. So bearing this in mind, the KPIs of optimization are again still the same: capacity, quality of service, and economy. We want to maintain optimal network in terms of all of these KPIs, but their formulation means their quantification is the issue. Okay, so I won't go into much detail, but just to give a few insights. For example, if we talk about capacity, the typical quantification of throughput would be this: receive signal level at any point. Means if there are two expressions, one for relay station, other for base station, and you're summing it for all the carriers or all the users, and RSL is the received signal level, classic throughput. And if you divide it by bandwidth, you're going to get your spectral efficiency. But you cannot optimize this parameter for 6 months, 3 months, because it will keep changing. So you want to optimize your frequency reuse, your number of sectors. So you need to optimize it for more relevant and more kind of determinable KPI. So with this notion, we need to come up with a metric for capacity. I should not use the term capacity because if anybody works in information theory, will kill me. But we need to come up with the notion for quantity of service we can provide. Our capacity is fine. Capacity, which which is a function of deployment architecture, FD, frequency reuse and deployment, which means frequency reuse, sectorization, number of relay station, 3 things. FD means 3 things, keep in mind. Okay, so we start with the simple expression. Okay, in that case, this sectorization, frequency reuse, and number of relay station will determine actually what the SINR distribution, geometric factor, as Mechanism mentioned, geometric factor. Okay, so at any point P, we will have F, which is a function of, in cylindrical coordinates, it is a function of distance from the base station, and very simple. I'm keeping it simple. And angle because there are antennas, distance because of the path loss. Okay, so if we plug this SNR values into Shannon formula and integrate it over the whole cell area, what will come up? We will come up with the average spectral efficiency throughout the area. Okay, maybe we can optimize this, but I'll tell you there is one problem with this. The first problem is it's integral, but we can change it with a summation, assuming that there are means all area can be represented as a set of points. Yeah. Yeah. Can I go to pick up glass of water? Sorry.
Okay.
Just a second. Let me switch. Thank you. Okay. Yes, please.
When you integrate over the surface, it's not missing D or something, because you are using angle and you are using you are using angle and distance, not XY. So
this is cylindrical coordinate. If you integrate over distance and phi.
Yes. So when you integrate, it should be D, 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 D phi.
I didn't get means we are integrating it over. Thank you very much. Yes, yes, sure. We are integrating it over distance and angle. Yeah.
Yeah. So it should be d phi.
Saying that if you convert dx dy into cylindrical, it's basically r d phi. So you're
Exactly.
increasing that r down to.
No, means I'm not converting it from anywhere. I'm starting from cylindrical coordinates.
It should be.
No, d is the radius here. D is the radius here. It's
Yes,
the
yes.
radius from the base station. Yeah.
When you integrate over a surface, it should be r dr d theta.
No, means it depends where it means. If we have, this was the least expected question I was expecting, but anyways, for example, this is the base station, okay, and D, and this is angle. Simply, if we integrate it over angle and also distance 0 to D, which is radius, we're going to get the cell area here. No? No?
The units are wrong already, but okay, if they're not.
Maybe, but I would like to know how.
You draw small, infinitesimal areas where it's straightforward. So the arc length is basically r d theta.
I haven't put any limits to avoid any confusion, by the way, but still, maybe you can explain.
No, I mean I can tell that this equation should be unitless, but it has a unit of 1/meter. Simply because you have the only terms which have a unit is d and the area. So you miss one distance term, which is exactly the r term. Yeah. So I can tell you that something is wrong, but I don't know. I remember there's an r.
No, I
somewhere,
get your
yes.
point. Yeah,
Yes.
but means I didn't get. Still, in the sense means you multiply with angular distance. Yeah, this is area, already area, and you are integrating it. It's already area. So units are not wrong. Maybe we can discuss it later. But the point is, we had to integrate it over the area. Okay, so that's why means A is there. Okay.
I mean, the one after this is okay, actually.
Yeah.
Yeah.
So
You get around the problem.
So that's why I put.
But I think you should correct it, yes.
Yeah, I'll think about it. But anyways, this is it's the point-based summation of area which we're going to use, not the integral anyway. But integral is there to tell us that we need to integrate over the whole area. Okay, but it's to make it more practical, we can assume there are areas consisting of course, points, and you can sum your the spectral efficiency at each point. The problem with that is we will have infinite points. There is a solution always for that. You can divide your area into bins, very small bins, assuming the S and R stays constant on those bins. And then B is the total number of bins multiplied by this small area, it should be the total area. If that's the case, then you can write your expression like this, which is you're getting spectral efficiency over the bins. I'll highlight the significance of this bin concept later. Okay, so now we have average spectral efficiency. This is summed over all the bins and divided by the bins. Average spectral efficiency over all the bins in the area, assuming that bins are small, very small. Okay, now if we go towards standard and assume that there is adaptive coding and modulation, and assuming that there are L sets of modulation and coding pairs, then we can derive the distribution of spectral efficiency in terms of bins, number of bins, like this. What here I'm trying to say is that your distribution can be worked out as a function of number of bins which are being served with particular spectral efficiency. It's very simple. Okay. And from the distribution you can get CTF. And threshold you can get from standard, or you can use Shannon equation directly. Okay. So to put it in a visual perspective, it will like means you have divided your area into small bins. Instead of B, I'm using A to show its area, and what you are getting here is actually expected value now. It's expected because it's the probability. This AL divided by AT is the probability of that particular modulation and coding pair being used.
What advantage are we exactly getting by converting integral to summation? Already that integral is probably not that hard to compute.
Yes, not
right?
hard, but it's not. It's in real world we won't have somebody to swap all the area. We'll have users. Okay, which is discrete.
But anyways, that's how you probably would compute the
Yeah,
integral.
but
Riemann
I'll tell you later. It relates to another contribution, which is about enabling coverage estimation. What we are trying to do here is we are getting a finite resolution, and each bin can be reported from. Okay. By number of users. Okay. Once they report their CQI back to user and back to the base station, and base station keeps logging the CQIs against that bin. In the end, the base station can determine the average spectral efficiency in the area. Okay. So this is more closer to the practical implementation than those integral. But still, if I would have started from this, people would have said, okay, why? It's just like integration. So integration is there as well. But this is the idea there.
In the previous slide, I think there should be PMF instead of PDF. It's just a...
Or maybe mistake. You can imagine that means 100 slides. Anyways, okay, but let's go back. So we have a measure of spectral efficiency which can be gathered at the base station, and it's dependent on the area. And this will actually dependent on your distribution of SI and R, geographical distribution, not the CDF or PDF. It's dependent on the geographical distribution of SI and R, and you can average it to see what you're getting in terms of, or vice versa, you can design the system to get particular average spectral efficiency using this. Okay, so we got one metric, but for area spectral efficiency, it's okay. Now we have quality of service and economy. Before going to quality of service, which is simple, I'll just show you the expression because it depends on this. Let's go to the economy. Economy means many things for operator, but here in terms of this optimization, it means energy consumption, EC, energy consumption. So we are trying to define a negative metric of energy efficiency, which is energy consumption. But it is power divided by that effective spectral efficiency. For example, a particular FD, frequency reuse and deployment, provides you a particular spectral efficiency, average expected spectral efficiency. Then this metric will tell you the joule per bits per hertz per site with this frequency reuse, with that number of sectors and number of relay stations. So, but what would be this P? P would be fixed power. Okay, fixed power per sector. Okay, variable power per sector, which is further function of antenna gain, which is further function of antenna material efficiency in this case, directivity of antenna, transmission power, and also the loading factor, gamma, respectively. Okay, omega, sorry, small omega. And similarly, we can have an expression for relay stations, which would be similar to this. So we need to kind of simplify, work out the expression which is more meaningful than this. So starting from the directivity of antenna will look like this if this is the form function of the antenna. But luckily we are able to simplify it for almost all the practical antennas by plugging in the vertical and horizontal beamwidth, which you plug in here. For practical antennas, it's almost 10, around 10. So you can, for vertical beamwidth, you can use this. And for horizontal beamwidth, it depends on the number of sectors, which you can formulate like this. S is the number of sectors, and alpha is overlapping among the sectors. Means practically sectors have a little bit of overlapping. Alpha is coefficient determining the overlapping. So once you have this directivity, you can write your EIRP as a function of antenna efficiency, directivity, and PT. This thing together is antenna gain G. Okay, this is transmission power. So from this you can get a desired transmission power, the amount of power you need to transmit with to get. You have a question? PD, desired. It means when you will plug it back in, it will become PT. But the reason I have put PD here is desired transmission power to get a desired EIRP. But it will, in this expression, it's PT. Getting my point? The reason to use PD is for a given, we'll start from the point, okay, we want a desired EIRP, isotropic radiated isotropic emitted radiated power. Emitted isotropic radiated power. Anyway, so for that value which you want to get, what should be the transmission power? This is, we start from here. Okay, this is the transmission power if this is your antenna efficiency and this is directivity. We have value for directivity. Efficiency is commercial value depending on the material manufacturing. You can use any value starting from 50% to 80%. We used 60%. Anyway, you plug those back here, and now you see you have power, which is function of fixed power, number of sectors per site, and number of relay stations per site. Here, the only means the noticeable point here is I'm trying to formulate the means identify the fact that sectorization gives you advantage in terms of gain, but it gives you disadvantage in terms of fixed power, and also maybe in terms of variable power. So there must be a trade-off somewhere in terms of power consumption. And if you link that, means plug this back to there, you have energy consumption metric, which is a function of number of sectors and number of relay stations. Okay, and impact of frequency reuse is coming to this spectral efficiency. So this way, this omega is actually a metric for power consumption.
Is it like closely related to area spectral efficiency kind of?
It's closely effectively area spectral efficiency, but I do another trick to get it apart actually. I'll tell you later. Because area spectral efficiency is good, but it has one problem, particularly with the advent of, we had this discussion how to define spectral efficiency. The problem with area spectral efficiency, no, this top expression you can recognize, this is that spectral efficiency we calculated, how base station can determine it based on CQ of users. But in the denominator there is a multiplexing factor. MF is multiplexing factor. Multiplexing factor is there for relay stations. When you have relay stations, you would gain some area spectral efficiency because of better coverage, but you will lose because you are multiplexing with them. So to take into account, that's in the denominator. And then frequency reuse, spectrum reuse factor. Either it's because of femtos or it's between the sectors. If you can get very high spectral efficiency if you have just one sector and no interfere, no reuse. So to have a metric which gives you a holistic picture including spectral efficiency and spectrum reuse efficiency, because these are two different kinds of efficiencies which we tend to be confused about. And so this metric here will give you a number which is taking care of the fact that if you have managed to get some spectrum reuse efficiency by frequency reuse or by using the relays, or spectral efficiency by power and sectorization and stuff. So this metric, it gives us effective spectral efficiency. I call it ESE, effective spectral efficiency, which you can later optimize. I'll talk about it later. Then fairness, notion of fairness. Notion of fairness, classically we have many fairness indexes, Jane's fairness index and blah, blah, but among the users. But here the fairness is a function of frequency reuse, sectorization, relay station, and as we have been shown in different plots, when you introduce femtocells, you need to, yes, there is a fairness within one, notion of fairness within that cell, but holistically there is a notion of service area fairness. Means from operator's point of view, they are interested in that as well. Means they don't want to have huge, highly service area with where they can use 64 com and the other areas where they are even able to not able to survive, make user survive on BPSK. So we need to, in terms of frequency reuse, sectorization, and deployment, the service area fairness is determined by that. You can determine your short-term fairness by scheduling schemes, but your deployment scheme actually determines your service area. So there can be multiple definitions. You can still put the Jane's fairness index here, but you have to link it with geographical location. But simply I'm using here the fact that how much my expected spectral efficiency, where is our, I'm using actually the PDF, the spread of PDF, standard deviation. How much is deviating from its mean value? Okay, so this number here will, if it goes up, service area fairness, it means I have fair service throughout the area. If it goes down, it means the deployment I'm using is not fair. And this energy consumption is coming from the expression previously. For more details, you can go through these two papers. So once we have this matrix here, we haven't become rocket scientists because we couldn't do much tough problem to actually. But again, we are able to have insights, some insights. What are the insights? Based on practical observation, you'll see means there are not infinite number of configurations you can have in terms of frequency reuse, sectorization, and relays. So based on your starting assumptions, you can have 26 different configurations. And since we have already driven the expressions, so we are able to calculate all the three metrics for all of those combination of sectors, relay stations, and service area fairness. For example, here, I don't have to go into detail for all of them, but you see that there is a trade-off. For example, you see if there are 6 sectors, you use frequency reuse of 3, and you put 3 relay stations there, it's optimal in terms of your effective spectral efficiency, but your fairness, service area fairness is low. And vice versa, if you want to have higher fairness, you have low spectral efficiency. But, and same is the case you will observe with the power consumption. For example, if you put more relay station, this is what? Relay station, active relay station. You put more active relay station. When I say active relay station, it means they have non-zero transmission power. Relay station, your energy consumption, fixed power consumption goes up, and with the similarly, you can have a graph for sectorization. So we need to see that the trade-off. But by looking at this and comparing different configurations, we'll see that none of them is optimal for all 3 of them, which is kind of intuitive. So what we need to do? What we can do, I don't know why it becomes a mess here. It was fine. Anyways, I hope I'm able to clear. We can, we can formulate problem, but I think we can just formulate problem. But if you formulate your problem that, okay, you want to maximize your ESC and surface area fairness and energy consumption as a function of frequency reuse, spectrum, and relay station, assuming that you have a system which can adaptively change number of sectors, switch off relay stations, and also can change frequency reuse. So this is a typical multi-objective optimization problem, which is nonlinear. Again, it's not it's difficult to say it's non-convex, but fortunately, it's combinatorial problem. It's just 26 possible solutions. Okay, so what you can do here is you can simply use general optimization, formulate it as a utility, linear utility, and you can give weights of your choice to each of the objectives, and these weights can actually be used to model operators policy. Here is where operators policy comes in. Means operators policy over the long term, which may prioritize energy efficiency, which may prioritize quality of service in this context, and which may prioritize capacity, or may a combination of them. And you plug in those values, and then you will see what is the optimal solution. I'll tell you later. Or alternatively, you can have a more sophisticated utility, which is targeted optimization. You have some target values to be achieved in, oh my God, what is that? Sorry. Target values to be achieved in each of the objectives, and then you can find the mean square error, and you can try to minimize this mean square error. Okay, so this is the notion how optimization occurs, but fortunately it's just, as you see, this is the table which shows the possible configuration. Even if you have more configuration, maybe even if you to go towards 100 configuration, still it's okay to have. This is expert system based optimization. You means in the base station or in the system you can have expert system which has a lookup table, and based on this analysis, any planning tool or even my simple simulator was able to evaluate these expressions. And then based on, for example, we start from where? Okay, these are the values evaluated for different frequency uses, but based on, say, this case. Here we say that, okay, our spectral efficiency is the most important thing, so is the fairness, but we don't care about energy because we are maybe in Gulf. Okay, that's fine. What is the optimal solution? It will tell you, okay, you need to operate in this condition. Okay, switch to this mode. And okay, and if you have a different scenario where your energy is most important, but you don't care about capacity, but you are conscious about fairness, then you will see this is the solution. So this way, actually by formulating the exact matrix as a function of frequency reuse and deployment factors, you can build an expert system which can quantify which can quantify the performance and can lead you to the optimal configuration. You don't have to just keep searching. Okay, that brings me to the very close towards the end of my solution. So here is just very simple result which gives the self-healing concept. It's not done by me, it's one of my colleagues' work. So I'm just presenting it here. It's based on his paper, which is uses fuzzy logic. The idea is very simple. The cell goes down and nearby cells can come in to help. And there is an algorithm behind it with a number of steps, but it's the simple most representation you can have. And in terms of performance, this is again, if you don't have any outage, with the outage this will be the gain, and with the normal operation this, but with that self-healing you will have better performance. You can read that paper if you are interested. Okay, end of presentation almost. I think I have highlighted most of the problems in the beginning, but to emphasize, it's important to relate the KPIs with the time scales of operation and design your solution accordingly which is agile enough for that particular time scale. And for that, we can compromise on some parameters. This actually helps you to be more realistic sometimes, as I said. And also, there is an important thing, which is mutual dependencies of objectives. For example, spectral efficiency is coupled with energy efficiency. That's why when we designed the metric for energy efficiency, we coupled it with spectral efficiency. You cannot simply optimize energy efficiency. The solution is that you need to shut down all the base stations. And solution for automating the KPI measurement process. Okay, I think I missed those slides, but here I think I can explain that. Automating the KPI process. The holistic framework which cellular systems need to come up with would look like something this. Mostly I have been talking about this part, but this is new part. Enabling self-organization. The problem is to kill the drive test, remove the drive test. We have actually one solution which I don't think I have time to present. Automate the coverage estimation process, which is possible now because there are a lot of user measurement reports going back to base station. And based on that, base station can build coverage map. And similarly, cell boundary needs to be estimated automatically on the base station. It's not like planning tool, which is offline. I'm talking about the real-time estimation of the cell boundary, because real-time estimation of cell boundary, for example, will help you to optimize the handover parameters because you know where is your cell ending. So there are a number of KPIs which need to be determined autonomously. So there is a need for algorithms for each of them to be developed here. And then once you have algorithm, we need to have some error and sensitivity analysis, which will tell, okay, for this kind of environment and shadowing and bin size and blah, blah, how much error your algorithm gives. Once you have this enabling framework in place, then you have this whole bunch of areas in front of you. Another area which is critical is you will find many individual solutions in literature, but what they're missing is that holistic picture. Means they have to work in the same system. It's not like load balancing will work in a different system and tilt optimization in another, and say frequency reuse and deployment optimization in others. And they have to work together in the same system. So there will be some parametric conflicts, there will be some objective-based conflicts and time scale-based conflicts. So all those conflicts need to be taken care of, and this is called self-coordination. So this has to be done by somebody. Okay, and yes, and also means, as I emphasized, there is less attention has been given to self-healing solution. So a more far cry as this comes to the solution. The question which was raised. Another paradigm for self-organization can be instead of relying on analytical information and stuff, we can rely on statistical information. For example, Google and Facebook are able to profile users, and they are actually able to tell you that when you are going to toilet and when you are going to home or when you are going where. So based on that, your activity cells can be optimized. Okay, I'll leave it. Okay, this is the list of parameters which need optimization, and these are the objectives for which they can be used. And from here you can see there is a lot of coupling. You'll see same parameters in multiple objectives. So if you are working for one objective, for example, you are maximizing capacity using transmit power, and then you are maximizing energy efficiency using transmit power, you are in trouble. You need to work out this. And the highlighted parameters tell you is the list which is kind of neglected in literature and can be needs some further work. Okay, yes. Suboptimality. Okay, there is a non-exhaustive list of tools for each kind of self-organizing solutions, and this is a wish list for me as well. Time is up.
All right.
Okay, thank you. Yeah, that's it.
Thanks. All right. Is that microphone on? Yeah, I think so. Can you hear me? It's on, right? Yes. Okay, Ali, I think you have done a really great job. 3 hours talking, that's already something very good. I'm not going to do my presentation. Brother, I would like to use maybe the last minutes to ask, what do you think of all this on stuff? What's your opinion, guys? Is that something which is useful? Are we mixing concepts? You know, maybe Harpreet, you have an opinion? No, you have no opinion. Okay, anybody has an opinion here? Ali, you maybe. Okay, can I first formulate my thought? I mean, we are. I think we are maybe mixing a little bit concepts here because we are invoking very often nature. Okay, we've been talking about the brain. We have been talking about schools of fishes, of flocks of birds, etc. This is on one hand talking about self-organization. Okay, on the other hand, we then try to optimize really the efficiency of a system. And frankly speaking, I think this doesn't go together. I think nature is not an efficient system. Nature is a reliable system. Okay, so we are designed to be very reliable, close to zero outage. In my opinion, every time you want to optimize your system for high reliability, then nature is a good thing. I mean, the machine learning is a proof. Machine learning works under conditions, you know, even if you have not actually thought about something, it will somehow work. It will learn it, the Q values will adapt, it will do the job in the end. We have, as a human, we have 2 eyes, we have 2 ears, you know, if we were an efficient system, we would have 1 eye, we would have 1 ear. You see what I mean? So we are designed for close to zero outage. Okay, but not for high efficiency. And I think if you look at our energy budget, how we are built, the joule as input versus joule as output, I think we're pretty lousy too. So I've been always very reserved about using natural principles of optimizing the efficiency of a system. All right, so in fact you will see that all the ant colony, there's a lot of stuff which has been, none of them manages really well. And in fact, what you do yourself is you go actually and use deterministic algorithms. You formulate the problem, you put capacity equations, you solve them numerically, integer programming, whatever, but you solve them again in a very deterministic fashion to resolve the efficiency problem, which I fully agree. So, but you know, my feeling is we are like, you know, mixing a little bit the concepts.
Mixing, but I mean, if you look at this wish list, it doesn't have any biomimetics here, but the tools are kind of, for example, the cellular automata. Again, you'd say it won't give you 100% optimal solution. Wherever you can find optimal solution, I think it's not reasonable to go back to nature. But where you cannot find a way around through your analytical tools, then you go for evolutionary heuristics. I think this means something is better than nothing. This simple principle, which we so it's not. Yes, we seek for efficiency, but when we cannot go for sky, we end up on stars. So this means if somebody is not looking for analytical or optimal solution and he's just directly starting with the fact, okay, I like birds and I want to stay with them. Maybe you need to go to school again. But if you try to find an optimal solution and you're looking at that, and you know that somehow you are able to see and prove that, okay, it's not possible, or even it's possible, it's not useful, it's not worth the effort, then you maybe means having 1 eye could be made us more efficient, energy efficient, but it could not be worth the energy efficiency because you'll be more energy efficient, but you'll die in 20 years age because of the accident, cars and stuff. So, you know, the reliability is compromise. It's a compromise again between the reliability and the peak.
Yeah, I'm just curious of to see where to draw the line. Really, I mean, you know, whether you maybe it's a good idea to say as long as you are able to formulate the problem, you should use like the deterministic approach. I call it deterministic approach with your equations and how you solve it is your business. But whenever you don't know the rules of the game, then probably some real nature-inspired approaches are useful, just as we have evolved. I mean, we as
Yes,
humans, as we are now, we are good, but it has taken us some bloody 4 billion years. You know what I mean? I don't want my base station to wait 4 billion years.
Yeah, of course.
So, we have taken our time. Sorry, you want to comment something? If not, there's Mehrdad who has also a question or a
Okay,
comment.
maybe I'll just take 1 minute.
Yeah, just use the mic, please, yes.
All right. So just the relation you are saying that the trick he has used and basically the examples he has given, it's a really good analogy. But again, it's a smart solution. We can't really say that it might be inspired by that, but again, even if you didn't know that the birds fly in a V shape, you could have come up with that intelligent solution without that as well. But as we discussed in the break, the coupling, so the deterministic solution is working because you have a deterministic spatial arrangement of the base stations. Now you move them a little, you perturb them a little. The coupling which you are ignoring, the one which I brought in the break, that will actually be significant. And in that case, probably your suboptimal solution would not be near suboptimal, because the triplets you are defining in a really special way. And that works only because there is a really good
grid
spatial.
is metric, yeah.
Exactly. Now you perturb them a little.
If you have a random grid,
Mm-hmm.
the question is, means there would be always few, means the amount of interference will decline.
No, I'm not even talking about random grid.
Neighbors, yeah. As you move further, maybe instead of 2, you will have 3 strongest
exactly.
neighbors.
So again, it's not like
you will be able to still cut down. The idea actually is, I think if I want to summarize the whole stuff in one sentence, is that you have to compromise on complexity to get optimal solution, or you have to compromise on optimality to get a practical and simple solution.
No, that's what my point is. So that's what we have been doing actually historically, and it's not something which I would say is inspired by birds. It's a smart thing to do, right?
Yeah, I mean that means if you look at this diagram, that's why means immediately after this you see this deterministic, and out of that I highlighted this multi-objective optimization, nonlinear optimization. Yeah, I'm not even touching learning or any of the heuristic throughout my work. Right. But what I'm trying to say here is, the reason I put that example here, one reason is that to keep the things light. Okay. Second thing is that you need to know that why you are knowingly going for suboptimality. Have you seen some similar solution working in real life? Yes. This is the solution which is working in real life. Okay, it's working. Yeah, and that's I think a paper in Science or Nature, which says that 70% gain in spectral efficiency. So, operator will kill a dozen people for 70% gain in spectral efficiency. So means we are not able to achieve that much, just 40%, but still we are able to. Something is better than nothing. If we have to go, even if we assume that we are able to solve the global problem analytically, then imagine that you have 2,000 base stations and you have to determine their tilts and use the distribution in all of them and calculate the center of gravities in all of the 2,000 cells, and then you would be able to set your tilts. It's similar to the back to the square one. Means by the time you will calculate that, the user would have moved. So that's the point. Means in the end, why we are researching? We are researching to have something working. It's not.
I like that.
Always use the local technology. That is, use the first smart step.
Yeah.
You get a totally broken.
Yeah.
Yeah, that's true.
Okay, so Mehrdad, yes. Yeah, go for it. Come on. Is it on the microphone? No, it should be working. Yeah, just speak closer to the microphone. Is it on? Just there should be a light on.
Okay. What I wanted to say was regarding, the definition of SON. Certainly, I think, characterizing SON is interesting, but at the same time, sometimes I feel that the differences between SON and classical and conventional notion of radio resource management is really marginal, and I feel like, both ideas are mixed together. Maybe that's why, for example, in case of, I think, when we are talking about efficiency and optimization, many ideas is still gonna fall inside the classical notions of RRM. And when, for example, sometimes this distributed nature of SON is confusing, but also in radio resource management, we have got distributed algorithms, but I think we cannot categorize all as SON. And still, I think characterizing SON does not give it a definite boundary between SON and RRM. So I don't know if there is any idea on what's the best way, for example, to just, I don't know, is it necessary to distinguish these two, or, and if so, what's the best way to distinguish these two?
I agree with you that the boundary is gray, but the reason we use this term is like why we differentiate physics from chemistry. It's the same question. When we started, there was no chemistry. Yeah, everything was physics. And now, if you dig down in any of the two of them, either physics or chemistry, you will see that again they are mixing together. So, if you look from very far or very deep, they are mixing together. But if you look from a reasonable distance, they are differentiable. For example, if you want to have a very comprehensive SON framework, you can't live without including RRM. Yeah, the classic RRM solutions we have is that again it's automation. But the element which makes SON is intelligence. Intelligence is second order adaptability. It's not the first order adaptability. I don't know I'm clear or not.
No, not at all, actually. What is second order adaptability?
Adaptability, for example, you design an algorithm for power control. Okay, in that algorithm you have one parameter which you optimized to give you maximum throughput. Okay, and you implemented it in your solution, and you optimized that parameter for a particular, say, cellular system ecosystem or base station height or particular set of assumptions. But when you leave that algorithm in the system for some time, the assumptions change and the ecosystem changes. Your solution is unable to change the parameter which was fixed initially. So that's second order adaptability. Means adapting the adaptive solution. Dynamic adaptability. This is one of the examples, but it's still not sufficient to differentiate the two. And the boundary is gray, just like the boundary is gray between any of the branches of science, because originally cellular systems are cellular systems, and they were not designed, or they haven't come into existence based on the fact that people will try to differentiate what is SON and RRM.
And NGMN has actually been very clear about it from day one. I mean, SON for them is nothing new. Okay, I said in the morning, it's an evolution of current concepts, and power control, as you say, or the scheduling is in a sense, a very early beginning of an autonomous decision taking. At the same time, I agree with Ali that a certain degree of intelligence should be there, which always means you're adaptable, to circumstances maybe which were not foreseen. Okay, and another definition I like, and I think maybe Anna Maria had it in there, but you didn't show it actually from the paper from Christian Beckstetter, said if a bunch of entities gets together and is able to achieve something jointly better than individually, that is already, it shows that your network has organized into something which gives essentially benefits. And the flying birds is a very good example of that. Now, I'm not sure I could find a good example of maybe the cellular network, but probably if you just took individual power control RRM as you have today, and you look at maybe the power consumption or the rates or whatever, and you sum it over the whole country, then probably implementing SON could essentially improve that by a given factor, order of magnitude or whatever. Okay, so that is an exercise which we still need to do for a lot of things. Yes.
What do you guys think is the difference between a SON and a cognitive radio network? Is it just like another term coined to write more grants, or does it really make sense? Now, of course, RRM is fine, but cognitive radio network and SON.
Actually, I had one slide which tried to differentiate between autonomous network, adaptive networks, cognitive networks, and SON networks.
But you had to take it out and you deleted it from your memory, right? Yes.
No, but the thing is, yesterday when Misha was telling me, he said they won't let you go through the first slide. So I thought this may be the one slide. which will take 3 hours, so I skipped that slide. This is great. Again, these cognitive terms start from a specific perspective. For example, the SON term started from here.
Right.
Removal of manual intervention was the slogan behind this. Cognitive started from the fact that there are white spaces. Okay, white spaces, and the term cognitive was kind of used to describe that opportunistic reuse. But no, the cognitive in itself is a broad term. If you look into dictionaries, you will see that it's same as intelligent and blah blah. But that was a specific use of cognitive, use case for cognitive. This is a specific use for SON. For autonomous system, the specific use are control systems. Okay, where you use this differential and
no, I agree. Philosophically, we can differentiate between,
but in cellular
anything.
System, still you can keep this means SON. Yes.
Well, I think if I can interrupt, I think it's very easy, really. I mean, self-organization is a process, and you can do this process by different means. Either you do it in a cognitive way, or in a more deterministic way, or whatever you come up with. You know, it's like if you want to go from point A to point B, you can take the bus, you can walk, you can fly. So one of the methodologies or one of the networking paradigms we can use is the cognitive one.
No, I'm not saying. Okay, I'm not speaking. I don't want to really differentiate between those two. It's not.
No, I think it's very good because SON is a general framework, and
no,
cognition
that's what cognitive people say also, right? That okay, whatever you can encompass whole wireless communications in cognitive radio networks because it's such a general term. And as you said, even you can have deterministic elements in cognitive as well. Like you put maybe your traffic statistics. Okay, at 12 in the night, you won't be having any traffic. Transmit as much as you want.
Yeah, it's a hybrid solution.
That is a part of.
It's a hybrid solution.
Exactly.
So yeah.
So it's a really thin line.
You can achieve self-organization by cognition, but also by other means. But cognition is in itself is just a sub part of the whole game.
Yeah.
In my opinion,
can be taken as a part of that because, again, opportunistic use will make your system smart, and it will achieve the same objective as self. And as a thumb rule, I think the terms which emerge later tend to be an umbrella for the terms which were older. So, means cognitive is an older term. So SON is the term which emerged kind of later and got momentum.
As I said, we started today with the SON framework. It's the same framework. Then we got a really truly cognitive presentation from Anna Maria, and now we got a more deterministic one from you. So you see, we're reaching all a way of organizing the network, making it more efficient, but via two branches, and you can have the hybrids, etc. Yes. Right. I think there were more. No, that's it. We call it a day. All right. Thank you very much. 7 o'clock, the bus. Don't forget.